Welcome to this lesson on the fundamentals of electricity, where we'll focus on resistance and how it affects current. To help visualize this, we'll replace an LED with a fixed resistor in a simple circuit. By changing the resistor values, we can better demonstrate how resistance impacts current flow. Resistance is a measure of how much a material or component opposes the flow of electrical current. It's measured in ohms, represented by the Greek letter omega. In a circuit, resistance works like a roadblock, slowing down electrons and reducing the current flow. Even in good conductors like copper, resistance exists due to imperfections in the material. These imperfections cause electrons to collide, reducing their speed and converting energy into heat. In this demonstration, we'll replace the LED with a fixed resistor to observe how changing resistance affects current flow. Using Ohm's law, we can calculate the current for each resistor value while keeping the voltage constant. However, we'll also compare these theoretical values to actual measurements to highlight real-world factors. We'll test three resistor values: 12 ohms, 120 ohms, and 1200 ohms. By increasing resistance, we'll see how current decreases in the circuit. A quick note before we begin. This is a simplified demonstration of Ohm's law. While theoretical calculations are based on ideal conditions, actual measurements can vary due to factors like component tolerance, contact resistance, and environmental conditions. Let's compare theory to practice. Ohm's law helps us understand the relationship between voltage, resistance, and current in a circuit. For now, we won't get into the details of Ohm's law calculations. That'll come in a later video. For this demonstration, we'll determine the current by dividing the voltage by the known resistance. In our first example, the resistor has a value of 12 ohms. With a 12-volt battery, the theoretical current calculates to 1 ampere. However, our actual measurement shows 0.760 amperes, highlighting real-world effects like component tolerances. Next, we increase the resistance to 120 ohms. The theoretical current is 0.1 amperes, but the measured current is 0.096 amperes, slightly lower than expected. This difference is due to additional factors in the circuit, such as resistance of wires and some of the connections. Finally, with a 1200 ohm resistor, the theoretical current is 0.01 amperes, and the actual measurement is 0.011 amperes. This demonstrates how small resistance elsewhere in the circuit can have a greater impact when overall current is low. Let's visualize this relationship. In our example, we saw that the voltage remained at 12 volts during the entire demonstration, so it will stay at a fixed value. The only things that will change are the resistance and the current. When resistance increases, as shown by the green arrow pointing up, current decreases, represented by the blue arrow pointing down. On the other hand, when resistance decreases, the blue arrow points upward, showing that more current flows. This is the fundamental relationship described by Ohm's law. In this lesson, we replace the LED with a fixed resistor to demonstrate how changes in resistance directly impact current. As we've seen, increasing resistance reduces current, while decreasing resistance allows more current to flow. These principles form the foundation of Ohm's law and are essential to understanding how circuits function. In future lessons, we'll dive deeper into Ohm's law by exploring series and parallel circuits, where resistance and current interact in more complex ways. We'll also look at more advanced calculations to better understand how these principles apply to real-world scenarios.